Good morning, everyone. So we'll start off with today's session. It gives me immense pleasure to introduce Dr. Sreenivas. Uh, Dr. Sreenivas Bhattiprolu is the head of digital solutions at Zeiss Microscopy and is based out of San Francisco Bay Area in the US. His team focuses on solving tough microscopy challenges by leveraging AI and deep learning technologies. Dr. Bhattiprolu has over 25 years of experience in microscopy. He received his PhD in material science and engineering from Michigan Technological University and earned his master's degree in physics from the University of Hyderabad. There's a really funny story about how he got into the field of microscopy. So during his undergraduation days in Hyderabad, he used to do a lot of sample preparation for a local microscopy facility. So he did his job without his parents' knowledge as he wanted to use the money to buy street food. Especially, he was very fond of pani puri. And with that, eventually ended up learning principles of imaging on a scanning electron microscope, which amalgamated into a journey of 25 plus years in the field of microscopy. So never underestimate the power of pani puri. Over to you, Dr. Srinivas. The stage is all yours.
Thank you for the introduction, Akshay, and thanks everyone for joining this session at a, I guess, relatively early time, your time. So hopefully you'll find this to be very educational for the next 1 hour or so. So let me go ahead and share my screen and jump to the presentation without wasting much time. So let's go ahead and share the screen. Okay, so at least Akshay, can you please confirm that you can see the screen?
Yes, I can.
Okay, thank you very much. So again, thanks for the introduction. And here is just a quick summary of what was just told. I'm part of Zeiss, the team of digital solutions, and our team is focusing on leveraging the latest digital technologies to make sure the image analysis, especially the microscopy-based image analysis community, can benefit from these tools. And I'll talk about a couple of these tools later on in the next 45 minutes to 1 hour. My background, I'm not a biologist, I'm not a life scientist, even though I have gained enough knowledge in the last 4 or 5 years of interacting with biologists, but my background is physics and material sciences and engineering. And again, like you heard in the introduction, for the past 25 years, I've been working with microscopes in the field of life sciences for the last 4 years. But prior to that, I worked in material sciences, geosciences, semiconductors, electronics, forensics, you name it. And I'm lucky enough to be exposed to these various fields, especially using microscopy, really helped me gain a lot of knowledge in how microscopes shed light in many fields. And just to start off by showing a image of myself, a picture of myself from 25 plus years ago. This was in 1994 when I was actually working at this one, not working at this place. I was like helping out someone with sample preparation and other stuff back in 1994. This microscope, this is a scanning electron microscope, by the way. And this was the make of this was Cambridge Instruments stereo scan. And this is Cambridge Instruments is now part of Zeiss. Well, for a while, it has been part of Zeiss. So looks like I have more than 2 decades of relationship with my current company, Zeiss, and I'm very happy about it. So this is a quick background of myself. And since then, I should say, from the time I started looking at the first image, I always wondered, how do we convert that image into information? Again, I think the entire theme of this workshop is Image2Numbers. So this is exactly what I was after for about 25 years. Okay, images are great, images are pretty, but what do we do with them? How do I convert that into a number that tells me something about the sample I'm looking at? Whether it is a semiconductor or electronics or life sciences based counting number of nuclei, whatever it is, just give me the information about the about what the image is trying to convey. So that has been my interest, and that led me towards a few areas. And recently I discovered the field of machine learning. When I said recently, I should say 4 to 5 years, and constantly amazed at how it can solve many of our image analysis challenges. So the plan for today, for the next 45 minutes or so, is going through a quick overview of machine learning. Of course, I'm going to talk about noise. That is the main topic here. So, but start with machine learning and then understand noise in images and ways to improve signal to noise, and what denoising strategies do we have. And this is where the machine learning fits in. And AI-based denoising on a peer, because not everyone is an expert at machine learning, and you should not be. I mean, you are experts at biology and your own respective fields, but how do you get your hands onto these advanced tools that are actually increasingly addressing our challenges, whether it is in microscopy or any other field? And I'll also provide a quick overview of image segmentation strategies, but again, because you're trying to go from an image to the numbers, and segmentation is one of the primary image analysis or image processing operations that you would perform on a regular basis. So with that, let's go ahead and start appreciating the field of machine learning. I mean, why do you care? Should you be even caring about this field? Yeah, some people over there with computer science knowledge are doing machine learning research, but as a biologist, should you be caring about it? If you look at this screen, you'll see that since 2000, of course, not many papers with the keyword machine learning published in biology field. So what you're seeing here is the number of publications in, this is from PubMed. So these are all like biomedical related publications. And as you can see, this is exploding. In the year 2020, you have like nearly 18,000 publications with a keyword of machine learning. Now, okay, is that a high number? Well, let's see how many publications are there with the keyword of microscope. And if you look at that, I mean, of course, these publications are also increasing in number, but literally in the last year, in 2020, the number of publications for using machine learning are much more compared to the ones with the keyword of microscopy. This tells us that, of course, microscopy is addressing the research in the field of biomedical, in the field of life sciences and biomedical fields. But machine learning is increasingly addressing, or at least being used as part of your life science research. So this gives a good indication in terms of whether you should care or you should not care about machine learning. Eventually, this is going to be part of our toolkit that's going to address our challenges. So I think it's a good time, if you already don't know much about machine learning, this is a great time to focus on this field and at least start to understand how it can be used as a tool, just like anything else. You probably are used to using Image2Numbers. You're probably used to using edge detection, algorithm. Along the same lines, I think it's about time to pay special attention to the field of machine learning. With that information, let's quickly understand what machine learning is, because it's a generic term, and I'm not going to a lot of details, but let me go ahead and explain what machine learning is. So it teaches the systems the ability to automatically learn and improve from experience. I know I'm just reading from the screen, but what that basically means is it creates a model, it teaches the system in terms of automatically learning this. So it's not like we're saying force equals to mass time acceleration. So it's not like we're fitting that to an equation and saying, okay, this is how you have to perform. No, it's actually learning based on the data that we are providing. The learning process, it begins with data that's either labeled or unlabeled. What do we mean by that? It's either supervised or unsupervised. Supervised means you're providing the system an image. In our case, it's an image or data, if you want to call that, and corresponding label, what that image is trying to convey. For example, it can be an image of a cancer cell and then label of cancer cell. It can be healthy cell and the label would be healthy. So you're actually providing both the input data and also what that data corresponds to as a label. if you're talking about segmentation, you're providing this algorithm, you're providing this image and the corresponding mask or segmented image. And this is called labeled. And unlabeled is where you're not providing that. You're just providing it data and asking the algorithm to figure out what the patterns are. So if you work with k-means clustering, for example, or any type of clustering algorithms, then you can you know that, okay, it finds patterns in your data. I'm just giving you at a high level. This is not a course about machine learning. I'm just giving you a quick overview of what machine learning is. And the third point here I would like to highlight is once the system learns, that trained model can be used to predict future data sets. Meaning, if you have a trained model for denoising your images, you can take that and in future only supply noisy images and get your clean images. If you have images and you have a model that does segmentation of these images, you just take that model and only supply your images, and on the other end, you get a segmented data set. So this is, in a nutshell, machine learning, and just look at how humans learn and how machines learn. And then we'll jump into the denoising topic. So this is how humans learn. You know that. I mean, we look at things and we're like, oh, okay, all these rounded things are some sort of circular things, and then now you can start identifying all the circles and so on. But let's look at the data. How do we learn about? How do we fit this data that you see on the screen? Well, first we draw a line and say, that looks pretty good, actually. You know, there's a good balance between data in the top, data points in the bottom. So this seems to be a good one. Now someone else walks in and they say, no, this is not good because I like this to be in a different direction. You see, now you also have some data points in the top, some in the bottom, but I'm pretty sure most of us think that this is a bad fit. And finally, someone else walks in and they say, hey, this is a much better fit for this data. Again, at this point, it's a matter of our opinion because we are saying, okay, this looks like it's a good fit between these data points. In our mind, we are doing the math of how well this line is falling in between these data points. We are doing a linear regression in our mind, right? Machines will do pretty much the same thing, except obviously they need a value to quantify. Again, talking about numbers, they need a number to keep track of. And in this specific example, what would be that number? If you look at this line is our approximation of our theoretical fit to these actual data points. So at this specific position, 0.45, if I look at that data point, if I follow this line, my data point would lie right there. That means there is an error between the real data and the fitted data right here. And what is that error? If you just assign some coordinates here, that error is nothing but y2 minus y1. Right? This error, the distance between this point and that point is y2 minus y1. You just add all the errors up for each of these data points. Well, you can just add the error because that will cancel out, right? So in this case, the value may be positive. In this case, the value may be negative and negative, positive. So you don't want them to cancel out. So you square this. So you take y2 minus y1 and you square it. And then you add all of these. And then you add all of these and average them. This is basically the definition of mean squared error. So we just saw, put together our equation for mean squared error in your data. And I'm pretty sure most of you know this. This is nothing but linear regression, and machines learn exactly that way. And if you do this in a machine learning way, linear regression is a form of machine learning. If you do that, then you'll use this mean squared error as a loss function, what they call a loss function. Any machine learning algorithm has what we call a loss function. And the goal of the machine learning algorithm is to minimize the loss function. In this example, for linear regression, its goal is to minimize the mean squared error. Why am I talking about a whole bunch of math and you are signed up to hear about denoising? I'm just quickly mentioning how machines learn. They learn by using some sort of a math. And typically, you have something called a loss function, which tells us how good or bad a fit is. And the machine learning algorithm changes the fit And every time it does that, it looks at the loss function. And if the loss function is going down, the value is going down, it keeps heading in that direction until it finds a minimum. And that is the solution. So this is how machine learning works in general. And now that hopefully you understand machine learning at a very high level, let's go ahead and see where machine learning fits in the field of microscopy. And again, there are many, many, many examples. I'm just going to show you only 3 different types of examples. One, it's a broad classification, in this case, called classification. There is segmentation, and there is other that I'm going to talk about in a minute. So when it comes to classification, think of this as usually referring to classifying an entire image. So you have an image that is infected, that's showing an infected cell, another image that's actually showing an uninfected cell. So this is a binary classification where you're trying to classify these images as either infected or uninfected. So this is again a machine learning problem, and this can be multi-class. It's not just a binary class. It can be, is this a mitochondria or not mitochondria? So this is a binary problem. You can have multi-class problem. Is this a mitochondria? Is this a lipid droplet? Or is this a lysosome? Or is this a nucleus? So it can be multi-class. And it can be obviously non-bio example. Is this a good part in manufacturing? Is this a bad part? So these all fall into classification type of challenges in machine learning. And the next one, probably most of you are familiar with, is segmentation. This is where it's referring to classifying at a pixel level. So you're classifying every pixel in an image, and you definitely know this. Again, are these pixels belonging to the sheep, or are they belonging to a dog? Are these pixels nuclei, or are these like cytoplasm? So this is basically semantic. What we call in machine learning, this is a semantic segmentation. Another variation of semantic segmentation is called instance segmentation, where you have, okay, I know this is a sheep, but this is sheep number 1, sheep number 2, sheep number 3, where individual objects are segmented. So you can get better metrics out of these. You can count the number of objects. So this is where probably counting mitochondria, detecting, counting, and getting the shape of these in your images. So that can be an application I can think of. So this is some segmentation. I'll briefly talk about it, but more importantly, I plan on focusing a little bit on what I call other here, which is image corrections and enhancements. And one of those is image denoising, where you have a lot of noise and you would like to denoise this. It can also be, for example, think of super resolution. You have a low resolution image and you want to artificially increase your resolution of your images. There is a machine learning algorithm for that, actually. There is a deep learning algorithm for that, approach for that. And one of the recent products that we released, well, this is has been a few months from Zeiss, is called AI Sample Finder. So where you just load the sample onto the stage and then it automatically finds the holder, and also the samples defines the areas. So you can define the experiment on the areas that have been detected, rather than just moving the stage, trying to find out and then define these regions. So it makes it much faster. Again, this is where we are using machine learning to power our typical workflow. So let's focus on the denoising aspect for the next 10-15 minutes or so. And I'm pretty sure most of you know what noise is, but let me just make sure we are all on the same page when it comes to the definition of noise. So I just took this right out of Wikipedia, and the definition is noise in images, especially noise in images. Noise, you find it wherever you have signal, right? It doesn't matter what type of signal, there is always some sort of a noise associated with that. In images, because they're visual, we can clearly see the noise right there. And how do they manifest here? Noise in images, it's a random variation of brightness or color information. I'm showing only grayscale images here, but it can be different colors also within the image. If I ask you, I mean, unfortunately, nowadays we are doing things in a digital way. These type of workshops are not better face-to-face, so I can literally ask you a question, which one do you think is acceptable? I'm pretty sure most of you would say the top left is not really that acceptable. Now, is this one acceptable in the middle? I mean, you do see some noise. Or is this one acceptable? Or the bottom right one? The bottom right is probably the best. The question of what is acceptable completely depends upon what you would like to do with the image. If you really want to post, let's say you're on a vacation and you took this picture, you want to post this on Facebook or Instagram, I'm pretty sure this image is good enough, the one on the top right. Yeah, it's showing you exactly all the details. It captures exactly where you are. It captures the mood, especially if it's in the if it's in color. So you know exactly where you are. So you're probably happy with that image. And if the acceptable means I would like to be able to segment the rock, segment water, sky, clouds, then maybe you would lean towards the bottom area. Bottom right would be ideal, but any of these are probably okay. So noise is inevitable, but how much noise is acceptable completely depends upon what you would like to do with that image. With machine learning, if you would really like to segment this image, with machine learning, you may be able to get good segmentation even with this top middle image right there. Maybe top left image if you push it, because machine learning is pretty good at learning both from the signal and from the noise. But again, the point I would like to make here is noise, of course, makes your images look ugly, but does that mean you lost your information? If so, what type of options do you have to clean this noise up? And that's exactly what we're going to look in a minute. But first, let's understand this noise further. Oftentimes, we look at this noise as signal to noise. Right? Signal to noise is a very good indicator in terms of how good your image is or the quality of your images. So in this case, let's draw a line across this G right there, the bottom part, and then look at how the waveform looks like. I'm pretty sure most of you have done this at least in Image2 or some image analysis program that you use. And as you can see, there is some noise in the background, and there's a signal right there, and more noise there, and noise down here. If you try to segment this image, I'm just applying simple Otsu thresholding for now. If you just do that, then this is how the segmentation would look like. In fact, I just did this a few hours ago in Image2. I just applied an Otsu threshold, and this is exactly what you end up with if you use this specific image. And my goal in this case, I was hoping to actually get this signal, these letters, segmented against this busy background. That did not happen here. Okay, so now let's increase the overall brightness of this image. So that's exactly what we are doing here. I just increase the brightness. If I go back, you see how the image is darker right there. If I go back up, the image is brighter. But increasing the brightness of image does not improve the quality of the information, because if you look down here, when I go back, of course, this entire thing increased, but you see that the noise increased and also the signal increased. So the signal to noise did not increase much. We did not get more informative images. It's basically the overall level went up. So if you segment this image, again, you would end up with a segmentation that almost looks identical to what I had before. So what can we do? The best way to get better signal to noise is either only increase the signal by keeping the noise constant or decrease the noise. So if you just decrease the noise, I mean, it's exactly the same. If you see the separation between the bottom and the top is exactly the same between this image and the next one. But here you can see that the noise is diminished by a lot, and you can see this very well. And if I do the Otsu segmentation here, then I get a very nice binarized image right there. So you can see that how you can go from image to information, or if you want to call this image to numbers, because now I have a very nice segmented image, and I can calculate the area occupied by my letters here and how many letters I have. So I can do all kinds of analysis now that I have a very nice segmented image. So how do we decrease this noise? Well, first of all, if you have a modern microscope, hopefully a Zeiss one, then we make sure that their noise is minimized at every point, because in a microscope, you have a lot of electronic components, and electronic components means you will have some noise associated with them. And we try very hard to minimize the entire overall signal to noise, maximize overall signal to noise, or minimize the noise in the system itself. Even if you have the best electronics, there is something called shot noise that actually comes from pure quantum mechanics, I should say. The quantum nature of these photons, because the photons are all of not the same energy that are excited from your sample. I'm talking about, in this case, LSM, confocal microscope. So the photons, the fluorescence photons that are reaching the detector, they're not reaching at the same time even to the detector, even though they're generated at the same spot at the same time. This is due to the quantum nature, and the noise that gets that's associated with this phenomenon is called shot noise. And this is luckily a random noise that we can usually handle using the deep learning technique that I'm going to talk about in a second. So, but even without using the denoising techniques, is there something you can do to collect the best signal to noise images? Yes, of course, you have a great microscope that gives you overall best signal to noise, but how can you improve this further? So averaging the signal is one option, increasing the source power, or increase the dwell time. What do we mean by that? So if you look at these images, the one on the left, no average, the one in the middle, 4x average. You can think of this averaging the signal as collect a frame, collect the frame again, collect the frame again 4 times, and then average all the pixels. Okay. Or it can be line by line, but either way, you're averaging it. I'm pretty sure most of you know that. You collect these images on a daily basis, so you know what averaging is. Also, 8 times average is on the right-hand side, and if you zoom in, you can see that, okay, noise, somewhat noise, less noise on the right-hand side. So averaging the signal is one option that you have to minimize or to maximize signal to noise or to minimize the noise component in your images. The other one is increase the laser power. Well, for confocal microscopes, you can think of this as laser power, but think of this as a source power. I'm not sure how many of you work with scanning electron microscopes, for example. They think of this as electron beam power. So whatever the imaging source that you are using, just increase the power. So for confocal microscopes, this means increasing the laser power, and this may not work all the time because of the nature of this fluorescence. So what's happening here is the use of too much laser power results in saturation of this fluorophores. Okay, so what's wrong with that? Well, as you probably know, that this gives a nonlinear relationship between the fluorophore and the concentration, fluorophore concentration and the detected signal. Whenever you have that nonlinearity, that means these images will not be ready for quantitative interpretation anymore. So you are limited to some extent by your laser power. So I don't know how to take the bar off on the top. I hope you're not seeing that. If not, I can move it to the side. Sorry about that. Another way of improving the signal to noise is by increasing the pixel dwell time. Previously, we averaged multiple frames or multiple lines. Pixel dwell time, increasing this is very similar. So at every spot, you're spending more time in collecting the signal. So here you have 2 microseconds, 8 microseconds, and 32 microseconds. Again, if I zoom in, you will see that you have more noise here, less noise, and even less noise right there. So if you have these strategies, why do you need denoising algorithms? Well, because for live cell applications, you may not have the luxury of increasing your laser power or averaging or pixel dwell time because of photo-bleaching and phototoxicity. And there are real issues for live cell imaging. Again, if you have done live cell imaging, I'm pretty sure you're nodding your head saying, yes, these are not the techniques that are available to you. You don't want to destroy your sample from photo bleaching and phototoxicity. So you have to resort to software-based denoising tools. So now let's look at what type of software-based denoising tools do we have. And until we find any of these, while we find a way to remove this noise and get the signal out of it, tease the signal out of it, we are going to miss out a lot of signs because it's hiding behind this noise. So let's see exactly what options do we have. And I should say, I just saw a couple of notes showing up on the screen, like your questions. So I'll definitely at the end of this take all of those questions, but please keep them coming. If you have any questions right away, when you think of a question, go ahead and type that in the chat, and we'll get to the questions at the end of this session. And I plan on, I should have mentioned this, I plan on this session for about 45 minutes to 1 hour, and then we can leave some time for questions. So jumping back in, so we were talking about the strategies to remove noise. And you'll probably relate to many of these. So on the left-hand side, I'm showing classical ways. And on the right-hand side, deep learning ways. And the classical ways, you probably have used Gaussian, median filter, maybe total variation filter. This is also very common in microscopy. And non-local means is common in computed tomography and MRI type of data sets. Same with block matching and 3D filtering. I absolutely love this BM3D. If you ask me to pick one filter, in fact, I want to pick two filters from classical approaches, I would pick BM3D for general denoising of random noise, and I would pick median filter for denoising salt and pepper type of noise. If you give me these two filters, I'm good in for a classical denoising. When it comes to deep learning, noise to void is the state of the art. I'm going to talk a little bit. So everything that's in bold right there, I'm going to spend a few minutes talking about these, just to make sure that we all understand exactly what these techniques are. Starting with Gaussian. Whatever filters, like if you think of Gaussian or median, and most of these filters, they're convolutional filters. So I would like to take a second to explain what convolution is. If you look at this image on the left-hand side, this grid, think of this as an image. Again, these are all different pixel values. 0 is dark, 245 is bright right there, and values somewhere in between 0 to 255, right? So this is our typical image. Now, how do I apply a convolution to this image? Well, to apply a convolution, you need to pick a kernel. The kernel can be a Gaussian kernel. That's when you get a Gaussian filter or a Gaussian denoising, Gaussian smoothing, whatever name you would like to use. Basically, when you refer to a filtering operation or denoising operation as a Gaussian operation, you're picking a kernel that has a Gaussian shape. I'll get to that in a minute, but let's understand, let's say this is my kernel, which is nothing but a 3x3 table matrix of some values. You apply this onto your original image. How do you do that? Basically, this is 3x3. So pick a 3x3 patch in your image and apply this. What do we mean by apply? You literally multiply them. So -1 times 170, 0 times 245, and so on, and add all of these. In this example, I'm getting a value of 394. What do I do with that? Well, replace the central pixel with 394. This is what a convolution operation is basically. Most filters that you see, digital filters, if they are working in the real space, they are convolutional filters. Sometimes you work in the Fourier space, that's a different bandpass filters. But these are all, most of the time when we refer to the real space filters, we are talking about this type of convolution. Gaussian is one of these. And once this filter is applied to this frame, it moves on. It moves, for example, by one step, in which case we call this stride equals to 1. If it moves by 2, stride equals to 2, and so on. This is how all digital filters actually work. Convolutional based digital filters work. Now let's look at Gaussian. Gaussian is one of those that has this, the kernel shape in the shape of Gaussian. Again, you're all into research, so I'm pretty sure you know what a Gaussian is. You probably saw that in 1 dimension, like a bell curve, and in 2 dimension, it looks like a hill where you have the central region, a peak in the central, and then it tapers off as you go down. And if you convert this into a kernel, let's do this, 1 sigma into a kernel. The central pixel has a value of 41. This is 1 sigma kernel. And as you move away from the center, the value goes down. The farther it is from the center, the smaller the value is. And I'm dividing each value here by 273. Why 273? Because when you add all of these values, it adds to 273. we do not want to add any unnecessary information to our image. So we would like to normalize a kernel. In this case, I'm dividing that by 273. So it's all normalized within this kernel. This is basically a Gaussian filter, and this is exactly how the Gaussian filter works. Now you take this kernel, 1 over 273, 4 over 273, 7 over 273, and so on. Apply that to your image, just move it onto your image, and then you have a Gaussian denoised image. And sometimes this Gaussian denoising is also referred to as Gaussian blurring or Gaussian smoothing, because by performing this operation, you are going to blur your images. So that is primarily the reason why Gaussian is not the preferred filter, at least not by me, for denoising operations. Even if you end up using Gaussian, please do not be very aggressive. I would just do 1 sigma, maybe 1.5 sigma, and nothing more than that. Now let's look at median filtering. Again, most of you probably know what a median is, but just a quick note here. This is an example from 6th grade or 7th grade, right? So housing prices. Let's say in, I don't know, since I'm in the US, I'm using these dollar prices right there. So the house values range from 350K to all 3.2 million. If you look at like housing prices in the news, they always talk about the median price in a city, the median housing price in a city. They never talk about the average house price. Because if you look at the average house price, you get 1 million almost. If you get a median price, it's $500,000. If someone says, hey, there is a nice neighborhood and the mean house price, average house price there is $1 million, I'm like, there's no way I can afford a house right there. But if someone says a median house price is $500,000, yes, I probably can convince a bank to give me a loan to purchase a house right there. So I'm pretty sure most of you know what median is, but I just want to make sure that we understand we're all on the same page here. So median better represents the data. And this exact thing is what we are going to use to denoise images that look like this. So median is an amazing filter if you would like to minimize or clean up images that has this type of salt and pepper noise, where you have wild spike, wild bright spot, or wild dark spot. And usually this type of phenomenon happens when you have bad electronics or something going on with your electronics in your system. So that's exactly when you see these type of noise. So let's go ahead and zoom into one small area, and you can see there are like 4 wild spikes in this region. How do we clean that up? Well, first let's just take our imaginary, image right here. And in this case, there is 1 pixel that is a wild spike of value 255. Everything else normal. So a median filter is again a kernel. In this case, let's apply a 3x3 kernel and look at the median values. So if you take all these values and arrange them and find the median of all of these is 140. And what do? We replace that central pixel where we are calculating the median and replace that with 140. You see how that bright region is completely gone, and now you have a very nice denoised image. This is how median filter works. And again, you probably know this, but it doesn't hurt to listen to these over and over. Now let's move on to BM3D, one of my favorite classical approaches for denoising. And as I said, this is, first of all, this was suggested in 2007 by Dabo et al. And go ahead and Google search for this paper if you are really interested in learning more about this. But let me just quickly explain this at a high level. This is extensively used, like I mentioned, in denoising tomography and MRI images, especially any time when you collect an image at very low doses. This can be very useful technique. And this is a non-local based technique, meaning this is not a kernel convolution filter like I just explained. This is not like our Gaussian. This is not like our median. That's why it's called a non-local based approach. So if you ever used NLM filter, non-local means filter, it's not exactly that, but it's the same type of principle, meaning first you find a reference patch. Let's say in this image, I want to select, or the algorithm selects this patch. And then it finds all other patches in this image that look very similar to this patch. And this is the principle behind it. So what does it do after that? So let's go ahead and look at this look at this image. And again, this is a two-step process. In step number one, again, don't be intimidated. This is very straightforward. And the first time I say don't be intimidated because the first time I saw this, I'm like, oh, what's going on here? You know, there's too much. But let's go ahead and look at the top left right there. So it divides your entire image. Let's say this is your entire image into blocks or patches. They call it blocks. That's why it is block matching and 3D filtering. So each of these is a block, and you have a reference block right there. And it searches for similar blocks and groups them. So you have a reference block, and it searches for similar blocks in your images or similar patches in your images and creates a 3D stack of all of these reference patches. Okay, and then it converts that from the spatial domain to a frequency domain. So think of this as performing Fourier transform to get from here to there. And then on the Fourier transformed space, it's going to perform hard thresholding and then converts it back to spatial. This almost sounds like bandpass filtering. It's very similar to bandpass filtering, like this part, except here it's actually putting together the stack of these blocks or patches. And it performs hard thresholding. Obviously, this denoises the image, and then this converts back into the spatial domain. And for each block, this is just one block I just gave you example. For each of these blocks, it performs an aggregate. I mean, it aggregates this to estimate the reference patch, basically. Yeah, to estimate the noise in the reference patch. So this is step number one. Step two is exactly identical. You see, step two looks very similar, except for two things. One, the reference is done based on the estimate from step number one. And the two, instead of hard thresholding, at this point, it's actually using something called Wiener filtering. And this Wiener filter, it needs information from step number one. It needs something called degradation function that it gets from step number one. Again, if you think this is getting too technical, that's okay. There are tools how you can use this, but it helps to understand exactly how things are working. And I definitely encourage you to go ahead and look up this document if you want to learn more about this block matching and 3D filtering. One warning here, or a caveat, I should say, is that this filter, BM3D, is slow. It can be very slow. So if you have large images, this can be very slow. That's the only thing. But it does an amazing job. I'll show that, in fact, right now. So you see, this is my confocal input image. And when I perform denoising, it'll go back and forth. And this is BM3D with a sigma of 0.02. And let's zoom in. Now, once you zoom in, you see some patches right there. I hope this shows up very nicely on your side. But as you can see, there is a lot of artifacts that are going on right here. And some of these, and I think I quickly read a question about who defines the block size. Yeah, you can define the size of this. You can define the size of this block. It depends on the implementation of BM3D. If you're actually implementing this yourself in Python, yeah, of course, you can define whatever you want. But most of the tools, wherever you can find this, typically you can define noise sigma. This is something that you can define. And patch size also is something that you can actually define. But I never had to think about defining a patch size because I let it use whatever the defaults that it has, and then let it go ahead and use it. And so far, I really never had to think about, oh, what should I play with the patch size? So just to be, but you can define it. Any non-local means, like for example, NLM filter, you define the patch size and also the patch distance or something. So these are the parameters you typically have. Again, as you can see, there are some artifacts right there, but then it did a decent job. But beware of artifacts. One thing you do not want to do when you do denoising is add additional stuff that's not there. You do not want to add information that's not there. This is science. You're doing research. You don't want to add artificial stuff. Now, if I change my sigma to 0.03 instead of 0.02, now it looks much even better, right? So this is 0.02 and this is 0.03. And if you zoom in, now you can see that, of course, things are a bit more blurred, but you can see this as a separate thing, and you lost some resolution there. obviously what you see here is a bit more blurred version and some artifacts right there still. I'm nitpicking here. This is doing a great job, but beware of some of the artifacts. It's not just this algorithm, any algorithm that you end up using, just look for artifacts. And in deep learning, you tend to have less artifacts based on my experience compared to the traditional classical approaches. So talking about deep learning, let's go ahead and briefly talk about this deep learning based approach. And in this case, most deep learning approaches require pairs of noisy and clean images for training. What do we mean by that? You have some deep learning architecture. And like I said, these are all supervised learning, which means you have to provide your image. And in this example, we're also providing a noise-free image. So a deep learning approach means you have a noisy image and an equivalent version of noise-free image, and you have thousands of such images, and you train a deep learning algorithm in terms of understanding the noise, and then you train a model. This is how most deep learning approaches work. And if you're curious, this architecture that you see on the screen is called autoencoders, where an input image is compressed to a small vector, and then it's decompressed to the original size. These type of architectures are there to reconstruct an original input image, but we are going to trick this by providing a noisy image as input and a clean image as an output. I'm not a big fan of this approach for a couple of reasons. First of all, there is another approach, by the way. This is just an autoencoder. Another approach called noise to noise, in which case it does not require a noise-free image, but it does require multiple versions of noisy images. A noisy image with some noise, another noisy image with more noise. So then it learns exactly how the noise looks like. So that's called noise to noise approach. It still needs images with different noise. For some samples, like for example, in confocal, you may not have that luxury of a noisy image and a clean image. Or a noisy image or a noisy image. This is exactly where noise to void approach that I'm trying to talk about. And later on this afternoon, our team is going to demonstrate that to you, walk you through that process. Noise to void is the approach that I'll be talking. I think this is the state of the art. In fact, this is the state of the art approach as of today when it comes to denoising microscopy images. This is developed by a microscopy group for microscopists. So you know that this is not some denoising algorithm that's designed to denoise nighttime photography images, but this is basically tested on confocal images, I should say. Okay, so here is the reference. Noise to void learns directly from noisy images, like I mentioned, without the need for clean images. And how does that work? And this is by the way, the Alexander Krull and Florian Hughes team. They do some great work, actually. Look them up, and they do amazing work in this field. So, like I already mentioned, it only requires noisy image, no need for additional noisy or clean images. It actually works only with noisy images. It learns how the noise is from the noisy image itself. And how does that do that? Well, based on a couple of assumptions. Basically, the assumption is signal has a structure, noise does not. What does that mean? In an image, if you have a signal, actual signal, coming from an actual fluorescence region, that is structured. The noise is not structured, meaning you can predict a pixel within the structured region by looking at the surrounding pixels. But you cannot do that with noise. With noise, you cannot just pick a pixel and predict that noise by looking at the surrounding. By definition, our noise is random. So that's the assumption. If that is the case, then you can build a architecture. Again, I'll try to quickly explain this. For those of you who understand machine learning, you will probably appreciate that this, even if not, you can, I'm hoping it's easy to understand, which is, what did we talk about in a couple of slides ago when I showed you the autoencoder architecture? You have an input image, goes through the training process, and then you have an output image. In this case, since we only have a noisy image, we are saying my input equals to my output because I only have single image. If that's the case, If your input is your output and you train a machine learning algorithm, it will be so good at learning how to reproduce your input image, meaning it'll be very good at learning the identity function. Hey, I have an input, I'll give you an output. It's not cleaning the noise. So the trick that these guys actually used or proposed is, instead of supplying this entire input image, how about creating a blind spot? They actually created a blind spot at the central pixel. And then, this is basically remove the central pixel. Think of this, blind the central pixel and only look at the surrounding pixels. This way, it learns how to detect noise, because you know that the central pixel can be predicted by looking at the surrounding pixels for actual signal, but for noise, that cannot happen. That's the primary assumption. Signal has a structure and noise does not. This is the core principle of noise to void. So let me go to the next slide to explain this a little further. Hopefully, if you have any doubts, this may clear up. So this is our image, and let's pick a small patch right in this image. Again, it goes in a structured way, but let's just pick this. How do you create a blind spot at the center? We can remove that pixel, but what does removing pixel mean? We have to replace that with something. We can replace that with a value of 0. In this case, they proposed that, hey, let's replace that by selecting a random pixel in this image. It can come from there, it can come from here, it can come from here. Replace that at the central pixel. And use this modified image as your input during the training process of your machine learning algorithm. So this is what they proposed, and the modified image is used as input, and the target patch for training. The target patch for training would be the original input image with unmodified values. So this is the input. I hope I'm not confusing. Step 1, take this small patch, find a random pixel to replace the central pixel. So that's your input image. What is the expected output image? The expected output image is the original patch, unmodified. Okay, and the loss during the training, remember the loss, our good friend loss, this is what we are trying to minimize. The loss is the difference between your ideal versus what your model is proposing. That is your loss. It tells you how your error is. So the loss during the training is only calculated for the blind spot pixels that are masked. So again, I encourage you to read the paper if you really want to get even more details, and if you want to fancy yourself with some math, go ahead and do that. But this is the core principle of noise to void, and it works amazingly, amazingly well. And they proved that, they showed that on by comparing it with BM3D. Again, like I said, BM3D is a state-of-the-art classical approach for denoising. And if you want deep learning, I recommend noise to void as state-of-the-art, especially for confocal type of images. And as you can see, the big drawback of BM3D, for example, this image, 33 seconds. That's a long time to denoise that image. And to denoise this image using noise to void, the same image, it's only 1.3 seconds. You may ask, isn't deep learning slow? You probably heard that, hey, the training is happening over multiple days or something. Well, in this case, the training happens over a matter of, let's say, tens of minutes to a couple of hours, depending on how many images you have to train your model. But once you have a trained model on your confocal images, now you can use that model to denoise future images. And this step is pretty fast. It's a second in this example. And it's pretty fast compared to your BM3D. Okay, and now let's go ahead and compare our noise to void on the same image right there. So you can see, there you go, that's the confocal, and here is the noise to void. Let me go back and forth so you can see how it changes. Yeah, and let's zoom in. Now you can see no artifacts. Nicely, the resolution is intact right there. You can see these features. By the way, this is a denoising technique. This is not a super resolution technique. So if your original image does not have the resolution, you're not going to get more resolution by denoising. It's just removing the noise and leaving your resolution as is. So let's compare all at the same time. So this is my original image, and go ahead and look at this region and also that specific region over there. You can see that with the Gaussian, there is a lot of blur. but it did a great job in denoising. BM3D, a lot of artifacts with sigma equals to 0.02, with sigma equals to 0.03, less artifacts, but still some artifacts, and then a bit blurriness right there. And noise to void, you have very nice resolution right here. And you can see that practically no artifacts, at least no visible artifacts that you can see right here. So this is why I definitely, as you can see, I prefer noise to void, because I don't have to tune anything here. All I need to do is take a bunch of confocal images, noisy images, train a model, and now you have a model that you can use. With BM3D, obviously, you will find the sweet spot if you find, like one of you asked, if you find the right patch size, if you find the right sigma value, you'll probably find a good balance right there, which means you cannot automate this for multiple images. If you're collecting hundreds of images and you want all of those images to be denoised, for each of those, you probably have to play with these values to see where is the sweet spot, right? So that's the problem with classical approaches. Same with Gaussian and other approaches. With these deep learning, usually if your input data is diverse enough, your deep learning trained model is generalized enough to actually do a great job on more diverse type of images. So that's noise to void. And as you can see, in this case, this is a 4D image. You can see this is a three-dimensional time series that we have segmented, and definitely the image on the right-hand side is ready to be interpreted. Now, how do you get your hands on deep learning? Like, okay, this is great, noise to void. Now, where do you get your hands on noise to void? You may ask the same question with BM3D. Frankly, I have used BM3D in Python. Like, there are a couple of libraries, and I can definitely send you information on that if you're interested in that. But noise to void is again, how do you get your hands? There is no, I think there is a plugin in Image2Numbers, but I'm not sure if you. I haven't tried that. But what we have done at Appear, again, you'll learn more about Appear this afternoon with my colleagues Manoj and Prasida. Appear is a cloud-based platform. It's designed to make advanced image analysis tools like the one that I just showed you. It's designed to make that accessible to, especially to researchers who are not coders. So you can automate your analysis. And how do you get to Appear? Just, it's a cloud-based platform, so you probably already signed up. We sent some instructions, so it's www.appear.com. And I should mention that it's a free platform, meaning it's free for nonprofit, academia, and individual use. If there is anyone who is from non-academia, for-profit in the audience here, just get in touch with me about some commercial options when it comes to Appear. But if you're in academia, sign up, go ahead and use it. Since it's browser-based, you can usually, I definitely do not recommend using on mobile devices because the experience is not that good, but on any system, on any computer, just go open Chrome or any of your browsers and just start working on this. I'll quickly walk you through a couple of features here, but again, let's save bulk of the work for this afternoon. I'll quickly walk you through this, and then I'll talk about image segmentation, and then we can open this up for questions. So when you log on to Appear, you'll see we have public modules, public workflows, machine learning right there. So when you click on public modules, you can see, think of these as plugins if you want, or apps. There are a bunch of modules that are developed by the community or developed by Zeiss or developed by our Appear team. And you can easily locate like these denoised modules. Like this one is pre-trained on a whole bunch of LSM images, confocal images. This one is pre-trained on a whole bunch of electron microscope images. And this one is the inference module. So you can, and we also have a training module. So if you don't like any of these, you can supply your own confocal images and get your own trained model that that captures the essence of your sample and your microscope personality. And you can create your own workflows. Basically, a workflow is, okay, you have modules, you put them together to create a workflow. Again, Manoj will talk about this later this afternoon. And you just put them together and you run the workflow, it runs it in the cloud, and you have your data there, you can download it. And also when it comes to running this noise to void module on Appear, I'll just show you a quick snapshot. Again, Manoj will do a good job in walking you through this. So you will be searching for modules, putting together your workflow, or you can actually search for a workflow directly, identify the one you want to run, for example, denoised, pre-trained, let's say end-to-end workflow. With end-to-end workflow, here you're doing both the training and the inference process. And anytime you run a workflow, just go ahead and check that you're using the latest version of modules, because whoever developed the modules are constantly pushing new versions. So maybe the latest version is the one that you would like to use. So let's go ahead and drag and drop an image. You can store up to 100 gigs on Appear, so you can use your own files on Appear and run the workflow in the cloud. Okay, so now let me quickly touch upon a couple of slides talking about semantic segmentation, because this is, again, another task. There's a reason why I'm spending time on denoising and segmentation, because at least most of the people I talk to, these are the two things that they do a lot when it comes to image processing. And then you have your own workflows. So semantic segmentation, I want to highlight a key important aspect, which is, do you really need machine learning? Completely depends upon your specific challenge. So if your image looks somewhat like this, very simple, you don't need machine learning. You just need Otsu thresholding. What does Otsu thresholding mean? In a histogram, it gives you one value. There is only one parameter that says, hey, your image goes from 0 to 255, and I think we are good if we separate the image at 127 pixel value, right? So you have one parameter, because this is a simple example. What if your sample is complex like this? This is a computed tomography image right there, and you see very faint features, and you have multiple different types of regions, and you want to segment them into 2, 3, 4 different classes. This is not as easy as just pressing an Otsu or some sort of an auto thresholding button. Here you need some sort of a machine learning, but maybe not deep learning. If you are a Zeiss user, you probably know of IntelliSys, which is a machine learning based image segmentation. It does an amazing job for 95+% of your samples, I should say. And this is traditional machine learning, where you extract features and then use a classifier to segment your images. So this uses about, let's say, tens to 100 parameters that you need to define. Remember, in Otsu, you have one parameter that you define. In a traditional machine learning, you have about a couple dozen to 100 parameters. But what if your image is more complex? Here, if I want to segment mitochondria against a very busy background, the complexity is coming from the background. Look how busy the background is. It makes it near impossible for us to automate the segmentation process of mitochondria. So here we need a lot more parameters, typically 1 million or more parameters depending on the complexity. And this approach falls into the category of deep learning, where UNIT is a great example for semantic segmentation for biological materials. This is exactly what we use on Appear. For our segmentation, UNIT is an architecture, but we have heavily engineered it to customize it for microscopy or scientific images. Unfortunately, this deep learning is accessible mostly to AI engineers and advanced coders, and this is exactly where Appear fits in. We made this accessible to everyday users. So all you need to do is go ahead and annotate. Again, you learned that this afternoon, and once you have your images annotation ready, that's the slowest part. Then you can just say, hey, I want to do semantic or instant segmentation, click the button and go ahead and train the model and segment it. You can segment it in the cloud, on Appear, or you can download the trained model, segment it in Zen, for example, if you have IntelliSys. Okay, and here are some of the examples of segmentations that we have done. This is a binary segmentation. This is an instant segmentation where each mitochondria is independently separated, and we can size them and all that. Then here is a multi-class segmentation where you can see multiple classes that are segmented. All of these segmented using our Appear machine learning tools. And finally, after all of these, I mentioned when it comes to BM3D, I did this myself in Python, and I know most of you are probably not coders, but if you're thinking about coding, I should just give a plug to our YouTube channel. If you can go to YouTube and search for Appear_micro, there is a playlist where it walks you through. Each video is probably somewhere around 20 minutes to 40 minutes, depending on the topic, but it walks you through absolute basics, assuming that you know nothing about coding, and all the way to deep learning. This is about, so far we have 127 videos, as you can see, and this is a nice way. If you are really trying to add a skill, add coding as a skill, you can go ahead and subscribe to Appear Micro, and then look at these videos, or any other videos if you want to learn more about Appear. So with that, let me go ahead and end this and open this up for questions. Thank you, guys.
Thank you, Dr. Srinivas. We will be taking questions from the chat box, and after that, if any participant has any question, they can either type in the chat box or directly unmute. Okay, so now Tanya will be taking the questions.
Thank you, Akshay. The first question is, the ways to improve the signal to noise will work for all type of experiments or samples?
Yeah, I mean, like I mentioned there, the ways to improve the signal to noise, literally, these are the basic tricks, right? I mean, if you're taking even a picture with your camera, right? I mean, if you have this SLR camera and at nighttime or evening time when there isn't much of a light, or if you want to control the light, these are pretty much the same strategies, right? You either increase the power, meaning increase the amount of light by adding the flash or something, right? So you're increasing the power, laser light source, for example. So that's why you have a flash on your camera. So you can increase the amount of light, so you get like more signal and you get more signal to noise. Or there is a chance that you can actually increase the dwell time, meaning you can leave the shutter open for a long time and then you can collect more signal, or you can actually do multiple exposures and average and all that. So these ways to improve signal to noise will work. I should say most type of experiments, but like I already mentioned, they may not work for live cell imaging, because for live cell imaging, your sample may die if you follow these strategies. Yeah, so I hope that answers that question.
The next question is, could you please highlight on which denoising method to use at watch instances?
Yeah, that's a good question, right? I mean, so the primary thing that I like to use is median filter is very straightforward. If I see wild spikes, if I see the salt and pepper type of noise, I always use median filter. I don't even think twice, right? I mean, just use median filter. It does an amazing, amazing job. No need to think of machine learnings and all that stuff. If you have a random noise like the one that you see, that you saw, from other images, if it's random, then there are two approaches that I always think about. One is, do I want a classical approach or do I want a deep learning based approach? If I have a dozen images with noise, if I have confocal, like about 10 to 15 confocal images or any noisy images, then I would definitely use noise to void approach. Because it's general enough. You'll be surprised. Noise to void actually works for even like low light photography images. So this is a very robust way of denoising images, the machine learning approach. I would try block matching and 3D filtering if I want to lean towards classical approaches, especially like I said, if I'm working with computed tomography or MRI type of images at low doses, I would use BM3D. Total variation is also a good filter. Actually, I recommend trying that total variation filter. That also works very well. So to answer your question, for confocal images, I would always think about noise to void. It actually works great. For even for wide field, even for scanning electron images, scientific images, I would definitely recommend that. But if you have one image that you would like to denoise, you don't have 10 images or 15 images, you have like one image that you would like to denoise, try BM3D or try total variation filter. So those may work very well. But I really don't go much fancy and then try a whole bunch of things. I used to use Gaussian filter. Again, if I if I don't care about resolution loss a little bit, Gaussian is the fastest. You just click the button and instantaneously you have the result. So Gaussian will clearly, tell you, give you the feedback instantaneously. So Gaussian is also useful. I know that's a very long, non-specific answer, but it is the reality. That is how at least I make my choices when it comes to denoising.
Okay, thank you. Another participant asks, if the signal in the image is bright, accompanied with noise, will denoising the image lead to saturation of the bright signal which was present?
Not unless it is already saturated. At least based on my experience, I mean, I think I know exactly what you're talking about here. Basically, okay, you have a bright image, and if in that bright image your real signal is saturated, then of course you will end up with that saturated image. Yeah. So in other words, most of these denoising operations, they are not adding any more intensity to your images. They are trying to work with the noise and they're trying to remove the noise. If you look at even the Gaussian kernel, right? So what is this Gaussian kernel? You have all these numbers and you're dividing by 273, I believe, whatever that number is, meaning that is a normalized kernel. And there's a reason why it is normalized. If it is not, then you're adding some information. You're adding the brightness. You're changing the pixel intensities as you're applying this. So most of these approaches, they are proposed by keeping that in mind. So in my experience, the image will not be any more saturated than it already is. Especially, I have tested this on confocal images using noise to void and BM3D and other approaches. It may appear that it is, because once the noise is removed, the image appears a bit nice, popped up, right, with all these colors. But usually it's not any more saturated, like I already said. Yeah.
Thank you, Dr. Sreenivas. If any participant has any question, kindly unmute and ask. Yeah. There's a question in the chat box. In CSLM, imaging of some protein comes as tiny puncta. In such, how the denoising work to distinguish between the noise and the object?
Yeah, if the resolution is, if you're a tiny puncta, I may have an image of that somewhere, but let me not search for that. But absolutely right, again. But the tiny puncta, unless these tiny puncta are 1 or 2 pixels, then you have to increase your magnification. If it is 1 or 2 pixels, then it is really difficult for us to tell the actual objects apart from the noise, right? I mean, but if they are agglomerate of at least 10 pixels or more, right? Now you know that these are real objects and this is not random anymore. So at a pixel, that's not a random. That's part of a structured object. So I have done this on these tiny silica balls. I think they're very small at low magnification and so on. But if the magnification is too low, then there is a good chance that, yeah, they may appear to be random. But the assumption is that you have structured and you have unstructured random noise. And noise to void, at least for sure, works on this unstructured part. But if your structured parts are trying to blend into this, then it doesn't matter whether you use Gaussian, whether you use median or any of these filters, you will have the same problem, which is your real objects being confused as noise. And I hope your real objects are more than a couple of pixels. I hope they are at least 20, 30, 40, 50 pixels. They may look small, but compared to the noise, if they are, let's say, bigger, then there is a good chance that they are not suppressed.
Thank you, Dr. Sreenivas. So, we'll end the session now.
Actually,
Yes, ma'am.
can I ask a question?
Yeah, sure.
Yeah, of course.
Hi, Srinivas. Thanks for the nice lecture. So actually, I have 2 questions. I was waiting participants should ask more. So the 2 questions are slightly different. You can answer separately also. So the model that we are generating for denoising, So can it be used for any, say, if I'm training a model with an LSM confocal, and can it be used images coming out of any confocal machine? That is question number one. How I can make it more generalized? Should my ground truth or the training, the way that I should be using various samples? That is one thing. The second question is, what is the advantage of machine learning approach over the classical denoising methods? With respect to denoising, my question.
Yeah, good question. So let me answer the first one, which is, I mean, to generalize this for your confocal in general, the way we trained our model, I mean, I showed you a quick snapshot of noise to void pre-trained LSM module on Appear, which you'll see later on this afternoon. The first release that we have done, it was trained with, I think, 40 images or something from a confocal microscope. Then we got more images from a different confocal microscope. Then we got more images. So we constantly train that by getting images from not just from different confocal microscopes, but collected under different conditions, different samples. So the best way to generalize a deep learning algorithm is doing exactly that. Now, if you train your algorithm, we have actually, even with the first 40 images or so from a confocal, we found that it's working amazingly well on images coming from a different sample, a different microscope. So this is surprisingly a very robust deep learning algorithm, I should say. But just because it's working fine doesn't mean that's the best way to generalize. Part of your first question was also about what is the best way to generalize it. The best way to generalize it is ask your friends for images that they are collecting on their confocal microscopes, and then just get all the, it doesn't matter what these images are. All it matters is, hey, these images are different and they have different noise signature. These images are different. Add all of these. So the more generalized and diverse the training data is, the more generalized your machine learning algorithm. That's true for anything. That's true for noise to void for sure. And that's true for any machine learning algorithm in general. And unfortunately, I mean, there was a talk by the people who invented deep learning from Stanford here about a few months ago, and they were talking about how machine learning, the deep learning, has a overfitting problem. What that means is you train a model on some data and it works great on that data, but it doesn't work great on any other data. This is the overfitting problem, which means if you are trying to identify some type of feature in a MRI image that is collected here in San Francisco, and you train a model on that, and you share that model with someone in Bangalore, and you're like, hey, this works on MRI data. I don't think it works on your MRI data because it's being trained on this MRI data, right? So this is where you collect one from Bangalore and all places, and then, okay, this is how these images look like, and generalize it, and then you have a much generalized model that works on all of these scenarios. So I hope that answers the first question. And could you repeat the second question? Sorry about
the second question is, what is the advantage of machine learning approach over classical methods of denoising?
Generalization, that's it. I mean, the advantage of the classical approach is it's tough to automate the classical approach. Let me put it that way, because you have to tweak certain parameters. The advantage of classical approach is you can tweak them and you can get whatever you want. But I'm not a big fan of that, because in research, you should not get what you want. You should get what the truth is. Yeah, so that's what research is all about. So that's why I'm not a big fan of classical approaches for these type of tasks, because then you can get whatever you want. You can get, hey, this time I want to use kernel size of 1.5. Oh, the next image doesn't look good to me. I want to use a kernel size of something else. With deep learning, you take the human out, because we all want to be a bit biased. We all want something to work because it fits our hypothesis. This is what we want, but that's not what science is. Science is what's the truth in your images. And the best way to do that is to generalize a machine learning model using multiple images and let this model do a good job in denoising it, and then or doing whatever that task, the machine learning task is, and then go ahead and take that image. So to answer your question, the advantage of deep learning is being able to automate the task and remove the human bias as much as you can. I'm not saying deep learning does not have human bias. In fact, deep learning also has human bias, because when you're feeding it with training data, that training data has bias in it, right? I mean, because you're getting it from your microscope or from someone else. So there will always be some sort of a bias, but with machine learning, you have a better chance of minimizing the even unknowingly introducing this type of bias. So that's the primary advantage. Being able to automate tasks is the primary advantage of machine learning. There is upfront time in terms of training, but once you train, the model can be used almost forever unless your process changes by a lot.
Okay, thank you.
Okay, yeah, no problem.
Thank you, Dr. Sreenivas. Thank you for joining us and explaining the mathematics behind what we were doing all along. Thank you.
Thank you.
Hi, Sreenivas. It was wonderful.
Oh, hi, Dr. Ravi.
How are you doing?
Good, good. How are you? It's been a while.
I noticed that you cleared a lot of noise out of this presentation.
Yeah, that's good.
Yeah, on a regular day, we would have been met in person, as you said, but these are difficult times and we need to adapt.
Yeah, hopefully soon we'll get to do this face to face again. So I'm looking forward to that.
All right. Thank you so much for taking time and putting your team together and, helping us understand a few more concepts more clearly.
Yeah, thank you for giving us this platform to educate people on the latest developments. Especially these are the ones that the latest developments in the last noise to void, for example, is in the last 12 months or so. So these the tools are rapidly evolving, so it gives a nice platform for us to go talk to you, the audience, about what's new out there. It's always exciting.
Thank you so much. I just wanted to say that we started the whole presentation, the whole workshop with image acquisition. So saying that without good images, you probably cannot do good analysis. And I think it's coming a good circle. In the last day, we have how to remove noise in spite of the best effort. So I think in that sense, I feel a sense of completion there. Thank you very much once again, and hope to see you soon in person. Take care.
Sure. Thank you. Thank you all.
Bye. Dr. Sreenivas, just a minute. So before you leave, I would request all the participants to switch on their webcam so that we can take a session screenshot.
Let us know when you're taking a picture, so at least I can put a smile on my face.
Okay, we are done. So for all the participants, yeah, just follow the instruction on the PP was sent to you yesterday and make an account on Appeal for the hands-on training session in the afternoon. Thank you, Dr. Sreenivas.
Thank you.
Thank you for joining us. Bye.